Programmable array logic is a family of programmable logic device semiconductors used to implement logic functions in digital circuits introduced by Monolithic Memories, Incorporated in March 1978. MMI obtained a registered trademark on the term PAL for use in programmable semiconductor logic circuits. The trademark is currently held by Lattice Semiconductor. PAL devices consisted of a small PROM core and additional output logic used to implement particular desired logic functions with few components. Using specialized machines, PAL devices were field programmable. PALs were available in several variants. One-time programmable devices could not be updated and reused after initial programming. UV erasable versions had a quartz window over the chip die and could be erased for reuse with an ultraviolet light source just like an EPROM. Later versions were flash erasable devices. In most applications, electrically erasable GALs are now deployed as pin-compatible direct replacements for one-time programmable PALs. Early history: before PALs were introduced, designers of digital logic circuits would use small-scale integration components, such as those in the 7400 series TTL family. The 7400 family included a variety of logic building blocks, such as gates, multiplexers and demultiplexers, flip-flops and others. One PAL device would typically replace dozens of such discrete logic packages, so the SSI business went into decline as the PAL business took off. PALs were used advantageously in many products, such as mini-computers, as documented in Tracy Kidder's best-selling book The Soul of a New Machine. PALs were not the first commercial programmable logic devices. Signetics had been selling its field programmable logic array since 1975. These devices were completely unfamiliar to most circuit designers and were perceived to be too difficult to use. The FPLA had a relatively slow maximum operating speed, was expensive, and had a poor reputation for testability. Another factor limiting the acceptance of the FPLA was the large package, a 600 mm wide 28-pin dual inline package. The project to create the PAL device was managed by John Berkner and the actual PAL circuit was designed by H. Tikwa. In a previous job, Berkner had developed a 16-bit processor using 80 standard logic devices. His experience with standard logic led him to believe that user-programmable devices would be more attractive to users if the devices were designed to replace standard logic. This meant that the package sizes had to be more typical of the existing devices, and the speeds had to be improved. MMI intended PALs to be a relatively low-cost part. However, they initially had severe manufacturing yield problems and had to sell the devices for over $50. This threatened the viability of the PAL as a commercial product and they were forced to license the product line to National Semiconductor. PALs were later second-sourced by Texas Instruments and Advanced Micro Devices. Process technologies: early PALs were 20-pin DIP components fabricated in silicon using bipolar transistor technology with one-time programmable titanium tungsten programming fuses. Later devices were manufactured by Cypress, Lattice Semiconductor and Advanced Micro Devices using CMOS technology. The original 20 and 24-pin PALs were denoted by MMI as medium-scale integration devices. PAL architecture. The PAL architecture consists of two main components, a logic plane and output logic macro cells. Programmable logic plane equals. The programmable logic plane is a programmable read-only memory array that allows the signals present on the device's pins to be routed to an output logic macro cell. PAL devices have arrays of transistor cells arranged in a fixed OR, programmable and plane used to implement some of product's binary logic equations for each of the outputs in terms of the inputs and either synchronous or asynchronous feedback from the outputs. Output logic equals. The early 20-pin PALs had 10 inputs and 8 outputs. The outputs were active low and could be registered or combinational. Members of the PAL family were available with various output structures called output logic macro cells, or OLMCs. Prior to the introduction of the V-series, the types of OLMCs available in each PAL were fixed at the time of manufacture. Each output could have up to 8 product terms, however the combinational outputs used one of the terms to control a bidirectional output buffer. There were other combinations that had fewer outputs with more product terms per output and were available with active high outputs. The 16x8 family or registered devices had an XOR gate before the register. There were also similar 24-pin versions of these PALs. This fixed output structure often frustrated designers attempting to optimize the utility of PAL devices because output structures of different types were often required by their applications. So, in June 1983 AMD introduced the 22V10, a 24-pin device with 10 output logic macro cells. Each macro cell could be configured by the user to be combinational or registered, active high or active low. The number of product terms allocated to an output varied from 8 to 16. This one device could replace all of the 24-pin fixed-function PAL devices. Members of the PAL-V series included the PAL-16V8, PAL-20V8 and PAL-22V10. Programming PALs. PALs were programmed electrically using binary patterns and a special electronic programming system available from either the manufacturer or a third party, such as Data I/O. In addition to single-unit device programmers, device feeders and gang programmers were often used when more than just a few PALs needed to be programmed. To refer to devices programmed in this way. Programming languages. Though some engineers programmed PAL devices by manually editing files containing the binary fuse pattern data, most opted to design their logic using a hardware description language such as Data I/O's ALL, Logical Devices CUPL, or MMI's PLASM. These were computer-assisted design programs which translated the designer's logic equations into binary fuse map files used to program each device. PLASM. The PLASM language was used to express Boolean equations for the output pins in a text file which was then converted to the fuse map file for the programming system using a vendor-supplied program. Later the option of translation from schematics became common, and later still, fuse maps could be synthesized from an HDL such as Verilog. The PLASM compiler was written by MMI in Fortran 4 on an IBM 370/168. MMI made the source code available to users at no cost. By 1983, MMI customers ran versions on the DECP DP11, Data General Nova, Hewlett-Packard HP 2100, MDS 800 and others. ALL. Data I/O Corporation released ALL. CUPL. Assisted Technology released CUPL in September 1983. The software was always referred to as CUPL and never the expanded acronym. It was the commercial first design tool that supported multiple PLD families. The initial release was for the IBM PC and MS-DOS, but it was written in the C programming language so it could be ported to additional platforms. Assisted Technology was acquired by Personal CAD Systems in July 1985. In 1986, PCAD's schematic capture package could be used as a front-end for CUPL. CUPL was later acquired by Logical Devices and is now owned by Altium Limited of Australia. CUPL is currently available as an integrated development package for Microsoft Windows. Device programmers. Popular device programmers included Data I/O Corporation's Model 60A Logic Programmer and Model 2900. One of the very first PAL programmers was the Structured Design SD20. They had the PLASM software built in and only required a CRT terminal to enter the equations and view the fuse plots. After fusing, the outputs of the PAL could be verified if test vectors were entered in the source file. Successors. After MMI succeeded with the 20-pin PAL parts introduced circa 1978, AMD introduced the 24-pin 22V10 PAL with additional features. After buying out MMI, AMD spun off a consolidated operation as Vantis, and that business was acquired by Lattice Semiconductor in 1999. Ultra introduced the EP300 in 1983 and later moved into the FPGA business. Lattice Semiconductor introduced the generic array logic family in 1985, with functional equivalents of the V-series PALs that used reprogrammable logic planes based on EEPROM technology. National Semiconductor was a second source of GAL parts. AMD introduced a similar family called PALCE. In general, one GAL part is able to function as any of the similar family PAL devices. For example, the 16V8 GAL is able to replace the 16L8, 16Hours8, 16Hours6, 16Hours4, 16Hours2 and 16R8 PALs. ICT introduced the PAL18CV8 in 1986. The 20-pin CMOS EEPROM part could be used in place of any of the registered output bipolar PALs and used much less power. Larger-scale programmable logic devices were introduced by ALL, Lattice Semiconductor, and others. These devices extended the PAL architecture by including multiple logic planes and/or burying logic macrocells within the logic plane, S. The term complex programmable logic device was introduced to differentiate these devices from their PAL and GAL predecessors, which were then sometimes referred to as simple programmable logic devices, or SPLDs. Another large programmable logic device is the Field Programmable Gate Array, or FPGA. These are devices currently made by Altera and Xilinx. See also, combinational logic, other types of programmable logic devices, Field Programmable Gate Array, Programmable Logic Array, Programmable Logic Device, Complex Programmable Logic Device, Erasable Programmable Logic Device. Field Programmable Logic Array, current and former makers of programmable logic devices, ALL, Advanced Micro Devices, Altera, ALL, Cypress Semiconductor, Intel, Lattice Semiconductor, National Semiconductor, Signetics, Texas Instruments, Xilinx, current and former makers of PAL device programmers, Data I/O Corporation. References. Notes, Berkner, John. Vincent Colli. PAL Programmable Array Logic Handbook. Monolithic Memories, Incorporated. Berkner, John. Vincent Colli. PAL Programmable Array Logic Handbook. Monolithic Memories, Incorporated. JDEC Standard JSD3C, Standard Data Transfer Format between Data Preparation System and Programmable Logic Device Programmer, June 1994. JDEC Documents.